Swayam Prabha. Digital India. Educated India.
Welcome back everyone, and in this module we'll continue our discussion on 3D statics, namely the problem at hand. So here we are having this object which is kept in 3D and it is touching the wall in the YZ direction, and along the X direction we have we have one point along the X direction. So let's draw this diagram a bit more carefully. So one point here, and then we have another point which is C, and then we have another point which is B. So A, D, D, B and C. Okay, A, B, right. So we have to find this component which is the wall normal reaction N of I. So then we see that, let us start to write the force balance. So the force balance will be N times I. We simply write the various forces plus X plus Y minus the fourth force is this weight minus mgk. Remember, this is a vector balance. We will have three components of each of these forces, and essentially this is three equations clubbed in one. And then we can write down the torque balance. So torque balance, and we see that for torque balance we see that this is AD cross N of I plus AB cross with Y, and so these are my torques. So we have to choose, we'll have to first fix the axis. We can fix the axis which passes through A, right? So in that case the torque balance due to the wall will be AD. So AD is that the perpendicular distance of this point D from the axis passing through A. So torque balance at corner. So this is at corner A. So we have an axis which is passing through A. So AD cross NI, and then we have AB cross Y. So this is the torque balance about the Y. So AB, and then plus we have, let's say, G being the center of mass, which is where the weight is acting. So we have plus AG cross with minus mgk, right? And we see that this is equal to 0, and we find that now let me call these equations by equation number 1 and 2, and what we see is we now start to insert the various numbers. So we start to insert numbers, whatever is given in the problem. We can all find all these distances AB, AD, AG and so on, and we will see that the various equations are as follows. So n times 6j minus 2k. So this is equation number 2. This is the torque balance, n times 6j minus 2k plus 4i plus 4j cross with y and minus mg 3i minus j. Okay, this is 0. Now if we look at the second equation, there are still 4 unknowns in total, but essentially 2 unknowns. One is the vector y, the other is this vector n, or a scalar n, right? So we have 2 unknowns, y and n, and the problem is we just have less equations. So what we do is we are now going to take a triple product, take a dot product or a triple we take a dot product of this equation number 2 with this quantity 4i plus 4j, right? So if that is the case, we will see that the triple product of this vector with itself will be 0, and then the contribution of y vanishes. So what we do is, we take a scalar product, we take a scalar product of equation 2 with the vector which is taken a cross product with y, which is 4i plus 4j, and now we can eliminate y. The triple product of a vector with itself will be 0, and we see that in this case n will be equal to mg by 3. We solve everything and we immediately get the value of n. So at least by choosing the axis cleverly, the axis of rotation cleverly, we can eliminate the unwanted unknowns and get the unknowns which we are interested in the problem, in this case the wall normal reaction. Okay, so let us now look at one more example to get a better understanding. So we have this is the case of a leaning rod, and we see that so what we see is, so suppose we have a rod z x, we have a rod zx, and then the rod is leaning. We have a rod A and the rod is leaning, right? And we see that this is let me write down the problem and then we'll draw the figure. So we have a rod, so we have first a rough floor. So why rough? Because we don't want the rod to slip on the floor. So a rough floor lies on the horizontal plane. On the horizontal plane, z is equal to 0. So what we have is the plane xy or z is equal to 0 is the floor, and then and the plane x equal to 0, which is the yz plane, is occupied is a smooth vertical wall. Smooth vertical wall is a smooth vertical wall. So then we have a uniform rod of mass m. We have a uniform rod of mass m and has its lower end on the floor, right? Its lower end on the floor at point 0, has lower end on the floor at point 0, and its upper end rests in contact with the wall. Rests in contact with the wall at point 0 BC, right? And then the rod is prevented from falling by having its upper end what has happened, the rod is prevented from falling by having its upper end connected to the point what are we given? Connected to the point 0, C by a light inextensible string. So it's a long problem, but again, we just have to carefully set up the force and the torque balance. So light inextensible string. And given the rod doesn't slip, given the rod doesn't slip, we want to find the string tension, and the wall reaction. We want to find the string tension and the wall reaction. Okay, so what is given is we have a rod which is kept its lower end at the floor. So the floor is at a comma 0 comma 0 and the point is at 0 comma b comma c, right? And now it is connected to the string at point, well, the string is connecting the string to the point, this is the point 0 comma 0 comma c. So we have a string, so which means that there is some sort of a tension here T. We can call this tension as Q here for the time being. And now we have to certainly find Q, the string tension, and we have to find the wall normal reaction. The wall is along the YZ axis, YZ plane. So the normal reaction P will be along the X direction. So Pi hat, and the Q will be along the J hat, the J direction, right? The tension. So this is minus Q J hat, which is along the opposite direction as the rod is going to fall, let's say forward. So again, we don't know which one is forward, which one is backward. We are just showing it for the sake of the diagram. The math will do its, will correct the sign accordingly, the math of the problem. Okay, so the problem is we have to find P, the wall normal reaction, we have to find Q, the string tension. So again, we write down the force balance. We write the force balance. We see that P of I minus Q of J minus mgk plus x. X now being the flow reaction. That is also an unknown of the problem, is equal to 0. And now similarly we can write down, let us say we can write down the torque balance. See, I don't want the unknown x. We only want P and Q in the problem. We are going to take a torque balance about point A so that x is cancelled. So torque balance about A, and we see that this is going to be 2L. So L being L is, so let us say the length of the rod is 2L, right? And the rod is kept along the direction n bar, right? So 2L n bar cross, we see that about point A. So cross Pi minus Qj plus Ln cross with minus mgk, and this is equal to 0. So this is the torque balance about the point A. And then of course 2L is the length, the rod length, and n bar is the unit vector along AB. And that is what we see. So now we see that we have written down the force balance, the torque balance. As usual, we have how many unknowns? We have 6 equations here, but we have how many equations we have? We have 3 equations of force balance, 3 equations of torque balance. So we have 6 equations, and we have how many unknowns? We have P, Q, X, we have 3 components, 5, and I think we also have L, which is unknown. We can essentially solve for the entire system, but we just need P and Q. So now to do that, we can find first P by taking the dot product of equation. Let's say the first is equation 1, the second is equation 2. we can take the dot product of the second equation with I. So now we have that is going to leave us with the scalar triple product n cross I n So if we take the dot product of equation 2 with I, then we will completely eliminate P, right? And then we will get an equation for Q. And similarly, if we take a dot product with J, then we will completely eliminate Q and we will get a condition for P or an equation for P, and that is how we solve. So what we have is, we have that, let us say we take a scalar product of equation number 2 with respect to I, and we see that we get 0 is, so we are writing in the triple product notation 2 times n comma pi minus qj comma I, and this is the triple product bracket plus n bar comma minus mgk comma I, right? And from here we see that we get q is equal to mg n dot j by 2 times n dot k. And we have sorted out, we have taken the triple product and we immediately get the value of q. So now notice now, so what is n? So we have to figure out what is n. The rod's position vectors are a and b. So I can see from here that the vector n is a times I plus b times j plus c times k. So that is my n, ai. Well, it is going to be it is minus a, sorry. So this is minus a times I plus b times j plus c times k, and then since we want this to be a unit vector, let us keep this to be a unit vector. We divide it with the total magnitude of the vector, which is the length of the rod, which is 2l. So we plug this expression for n onto the other this other factor q, and we see that this is mgb by 2c. We plug n dot j and we see that this is n, this is minus ai plus bj plus ck by 2l, right? And we see that this is what we have. So q is this. And similarly we can write the triple product. Again we take a scalar product of the same equation 2 with j, and we are left with an equation for p. So take scalar product of equation 2, which we have written in the previous slide, with respect to j, and what we find is p is minus mg n dot I by 2 times n dot k, and we see that this is mga by 2c. Okay, so that completes the problem on statics. Basically this is all what I have in statics. And in the next module, so let me just give a brief overview of what we are going to cover in the next module before we wrap up. In the next module we are going to completely ditch the classical mechanics point of view of solving all these problems, namely the physical point of view of solving all these problems in classical mechanics, and now we will adopt more mathematical approach. Namely, we are going to go back to the origin of Newton's equation through the so-called Lagrangian, and we are going to introduce the Euler's equation as well as the concept of Hamiltonian through our so-called calculus of variation. So some of the problems we will revisit, and while for others we are going to develop a more general theory where we now start to completely work in the space of generalized coordinates. So just to recap, what we have done so far is looking at the classical mechanics problem from the completely physics point of view, using Newton's the Newton's laws of motion, as well as its variants, as well as its conservation principles. We are now going to see another point of view, which is the analytical technique through the so-called calculus of variations, and this is going to be the second half of this course. So I would say that I would like to wrap up here. So thank you all for listening up to this module. Thanks so far.